A system is a coherent, interconnected set of elements organized to achieve a specific mathematical function. It is a structured architecture of nodes, valves, and loops. The behavior of that architecture over time, whether it results in growth, stability, or decline, is endogenous. In a significant sense, the system causes its own behavior. When an organization fails or a resource vanishes, the standard managerial reflex is to blame external forces. We point to an aggressive competitor, an unpredictable supply shock, or a sudden market shift. System dynamics offers a different lens, treating these failures as the logical output of internal structures. These pioneers developed a methodology to map the hidden forces that dictate systemic outcomes. Building a model from first principles allows us to examine how rational, highly optimized systems can produce unwanted results, like persistent oscillation or total collapse. The foundation of any system is a stock. A stock is the physical or informational memory of accumulations over time: water in a reservoir, the capital in a bank, or the inventory in a warehouse. A stock is governed by flows. These are the rates of change, these specific mathematical inflows and outflows that fill or drain the accumulation. This bathtub stock and flow model demonstrates dynamic equilibrium. The stock remains constant when inflows perfectly match outflows. Increasing inflow breaks equilibrium, causing a linear increase. But an instantaneous inflow spike doesn't instantly fill the stock. Stocks process change gradually, acting as physical delays. Stocks act as inherent buffers. They decouple inflows from outflows, embedding unavoidable phase lags directly into the fundamental architecture of the system. Systems manage these accumulations through feedback loops. A feedback loop is a closed causal chain, where the level of a stock controls its own rates of inflow or outflow. Trace the path of a reinforcing loop. Larger capital stock creates greater output, increasing reinvestment back into the stock. Pulling against it is a balancing loop, an equilibrating mechanism. Capital depreciation acts as a counterforce. More accumulated capital means more machines wear out, draining the stock. This time series graph plots a biological population governed by these same competing forces. It demonstrates the principle of shifting dominance, where a system's trajectory is dictated by whichever feedback loop is currently mathematically strongest. Initially, the reinforcing loop of births is stronger, driving growth. But as the population hits environmental limits, the mortality rate climbs. The balancing loop eventually overtakes the reinforcing loop, altering the trajectory from growth toward equilibrium. Complex behaviors do not require random external shocks. They arise entirely from the internal shifting of dominance between competing feedback loops over time. The information delivered by a feedback loop cannot change current conditions. It can only impact future behavior. This creates unavoidable friction and phase lags. This car dealership model maps operational delays: the perception delay to verify a trend, response delay to issue an order, and physical delivery delay from the factory. Following a demand increase, the stock depletes. The system initiates a wave-like correction as orders and deliveries seek equilibrium. A common managerial response is to dampen the oscillation by aggressively shortening the response delay. The mathematical reality is different. Since physical delays remain static, reacting faster to lagging data forces the system to overcorrect, generating volatile oscillations. This is a case of high leverage in the wrong direction. Optimizing local reaction times without accounting for structural phase lags often amplifies instability. When we connect the reinforcing loop of capital growth to a constraining balancing loop tied to a finite environment, the results are often sudden. In a stock-limited system like oil extraction, the resource does not regenerate. As the deposit depletes, extraction costs increase, forming a powerful balancing loop that strangles profit. This graph maps exponential extraction hitting an absolute depletion limit. Compounding growth requires escalating reinvestment, causing a production crash when extraction costs exceed yield. A massive discovery seems like a solution, but under exponential growth, quadrupling the resource pushes the peak back by only a marginal fraction. A flow-limited system, like a fishery, presents a different challenge. Operators deploy technology to improve their yield per unit of capital, finding fish more efficiently even as the population thins. Here, the capital stock continues its climb, while the resource stock drops below its regeneration threshold. Efficiency masks the decline until the resource can no longer sustain the harvest. In this configuration, local optimization masks the degradation of the macro balancing loop. When the resource fails, the capital stock has no way to recover, leading to a breakdown of the entire system. Why do rational, localized decisions aimed at optimizing growth so frequently trigger systemic failure? This often happens because operators attempt to manage specific flow rates while ignoring the delayed, nonlinear architecture actually governing the system. Systems must be understood as integrated wholes. We cannot manage the complexities of a macroeconomy or a global ecosystem by focusing on isolated parts. Effective intervention targets the architecture of the feedback loops themselves. While operators often focus on reaction speed, the leverage lies in the structure. Managing a complex system requires designing for delays, respecting the limits of balancing loops, and restructuring the operational rules of the feedback architecture. We cannot fix a system by treating its symptoms. Effective management requires engineering the rules, delays, and structural architecture that define how a system behaves over the long term.